Hello? 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 Can you hear me?
Hello?
Hello?
Yes, sir, we can hear you.
You can see the slide? You can see the presentation? Can you see the presentation?
Good morning, one and all. We once again welcome you all to the second session of the virtual workshop on computer-aided drug design. A kind request to the participants to mute their audio and video so that no mess will be created. Unnecessary chat should be avoided in the chat box. The participants can clear their doubts and ask their queries after the session gets over. The attendance link and the feedback link will be sent at the end of the session so that the participants can give their attendance and feedback. Now, Professor Mukesh Doble will take over the session. Sir?
Okay. Good morning, everyone. Okay, yesterday we talked about properties of molecules. They are called structural features, descriptors, properties. So just like we also have, human beings have properties like height, weight. Molecules also we can calculate properties of molecules. Things like number of hydrogen bond donors, number of hydrogen bond acceptors, molecular weight, polar surface area, log P, like that, almost 2000 properties. And I also showed you many databases yesterday. Okay, the most important one I showed is the zinc database, zinc 15. Can everybody see this screen?
No, sir.
Okay. You can't see the screen?
Yes, sir. Yes, sir.
Yes, sir.
Yeah, okay. So yesterday we saw the zinc database, which contains millions of structures, and it gives you some experimental properties or descriptors. Then I also talked about drug bank, drug.com, FDA. These are databases which contains information about drugs. Drugs means those which have been approved by FDA. Otherwise, when we are doing testing a compound in our lab, we call it a lead molecule or a hit molecule. We don't call it drug. It is called drug only when it is approved by the FDA in USA or in India, Drug Controller Authority. Otherwise, it's called a lead molecule. Okay, that's why it's called lead optimization, and so on. Okay, so the drug bank, drugs.com, FDA, they contain information about drugs, drugs which are in the market, even failed drugs also. So if one is interested in looking at a particular disease, you can start looking at those molecules. And then there are other databases also, ChemDB, ChemDBL, PubChem, and so on. And then I also showed you how to calculate these descriptors, because not many descriptor experimental data is available. So Swiss ADME is a very good server where we can calculate many properties of the molecule. Some of the properties are related to the bioavailability. I defined what is bioavailability yesterday. That is the concentration of the drug that reaches the target site as against the concentration that is given orally. We are talking about oral. Bioavailability is generally oral bioavailability, because as the drug travels on the way, it comes across the GI absorption, then solubility, then it has degradation by the enzymes in the liver. So many things can happen on the way. So the amount of drug available at the target site will be less. So that's bioavailability. So Swiss ADME gives a lot of information through calculation. It calculates log P values for known molecule, unknown molecules. Then it calculates something called ADME, absorption, distribution, metabolism, and excretion information. So that's a useful server to look at. Then I also showed you other things like ChemDes that also calculates some properties. Then there is OChem, which also has properties of a lot of molecules. Then I showed you the 3-ADMET. So it gives you information about toxicity also. All these are calculated. Okay, so these are not experimental, they're all calculated. So this pre-ADMET gives you information about, again, ADME details, drug likeness property, toxicity, and so on. So if you are designing a new molecule, you can look at these properties and see whether they satisfy all the conditions. And I also showed you many rules: Lipinski's rule, Muge et al. Rule, Ghost et al. Rule, then blood-brain barrier penetration, BGBF flags, so then polar surface area requirement, then Otira rule of 3. So many rules. So SPCET also gives you whether your molecule which you are giving satisfies all these conditions. So we can modify the structure. I showed you because they also have the drawing feature. We can modify structure and again recalculate some of these rules or properties again. So we can design molecules on the screen itself. Okay, so all these are useful servers for calculating properties of molecule, because ultimately many drugs fail. Almost 95% of the drugs fail, although it works very well in the lab, because of so many reasons, which I also mentioned about. So many reasons they fail. Okay, maybe poor bioavailability, maybe poor ADME properties, maybe poor distributions or absorption, solubility, or it may be having short-term toxicity, long-term toxicity, and so on. Actually. So many drugs fail because of that. Actually. So we need to simultaneously do and calculate, if possible, even experimentally determine. Generally, animal studies are done to determine some of those properties also, bioavailability and so on. Actually, but computational tools help us to do many things. Then I also showed you one software called OpenBabel, which can be used for converting files from one extension to another. That's going to be very, very useful, because Zinc will have a file extension as .sdf. So other softwares may require some other format. So we need to convert that. So OpenBabel is very useful for that. We'll look at it. Okay, so today we are going to look at the ligand-based drug design. Okay. Okay, I also introduced something called Smiles notation. Smiles notation is very, very useful for transferring structure information from one file to another, one server to another, or one database to another. So it's a text representation of the molecule. Okay, so it's very, very simple text representation of the molecule. Otherwise, we need to transfer the 3D structural details from SDF or mol or mol2 and so on. Smiles is the easiest one. So we can represent any molecule, whether it's got a single bond, double bond, it's got heterocycle rings, aromatic rings. So all these can be represented in the text form, which I showed. So you can read more about it. Okay, so today we are going to, there are two types of designs. Okay, can you all see this slide?
Yes, sir.
Yes, sir.
Okay, there are two types of design. One is called the ligand-based design, other is the target-based design. Ligand is your lead molecule or the drug which you are trying to discover. So ligand is a small molecule. Drugs are always small molecule. The other one is target-based. That means target protein or target enzyme. Okay. So in the ligand-based design, there are several different approaches. One is called QSAR, quantitative structure activity relation. QSAR, quantitative structure activity relation. Other one is called pharmacophore-based design. Okay. The third one is called fingerprint-based design. Okay. So we are going to today talk about this pharmacophore-based design, and tomorrow we will talk about the quantitative structure activity-based design for the ligands. Then the last day, we will talk about target-based design. That means I know the three-dimensional structure of my target protein. Then I try to design molecules which will go and bind to the target. Okay, so that's where we have things like docking and so on, actually, as you can see here, docking. So here on the ligand base, that's on the left-hand side, we will look today at the pharmacophore-based design. Okay. Once you design some molecules based on these, either ligand-based or target-based, and of course, we need to later on check the properties, ADME properties, drug likeness properties. That you should not forget. You may find some molecule based on these approaches, but they might not satisfy the Lipinski's rule or Go's rule or Weber rule or blood-brain barrier rule, GA absorption or oral bioavailability. So we need to anyway filter that. Don't forget that. So whatever you design, whether it's ligand-based or target-based or combination of ligand and target, ultimately we need to check the rules, various rules. So we need to use the software like SPCET or pre-ADMET to check whether all these properties are satisfied. So if it doesn't satisfy, throw it out. Finally, select molecules which you take it for your experimental studies. Okay, that is how the entire flow looks like. So we have the ligand-based design on the left-hand side, target-based design. If you know the target, yes, good. And otherwise, we have to stick to the ligand-based design. We can use pharmacophore-based design or QSAR, quantitative structure activity. So we come up with new structures. Then we check whether the new structures or new compounds which we are designing satisfy all the rules. If it doesn't satisfy, throw them out. Then finally come up with some candidates which satisfy. Then take them for your experimental, laboratory-based experimental work. And later on, of course, you may go to animal studies, human trials. That's much later. Okay. So we will today talk about this pharmacophore-based design for the ligands. Here also there are some free softwares which we need to use to do the job. Okay. Let me define what is a pharmacophore. It's a description of molecular features which are necessary for recognition of a ligand in a macromolecule. So ultimately a molecule or a drug goes and binds to a target. So it has certain features which will help it to bind to the target. Okay, the features that is called the pharmacophore or features. I'll tell you in the next slide actually. So the IUPAC says steric features, electronic features. So steric features means volume, size like features. Electronic means electrostatic things, potentials and so on actually. So molecules which show activity will have certain common features. And with pharmacophore-based design, we try to identify what those common features are. That is what pharmacophore-based design is all about, actually. So sometimes you see a diverse set of ligands may show activity for a particular cancer. You may wonder why. But if you look at the pharmacophore features, they may be having a common pharmacophore features. For example, again going back to, say, basketball players, common feature could be they are all tall people. So generally, tall people, basketball. So that is the pharmacophore, I would say. Okay, so, or maybe long legs. That will be a feature for a good basketball player. So same thing, a molecule, a set of molecules which show certain activity may have certain common features or pharmacophore features, which we try to identify using this pharmacophore-based model. Okay, so tall persons is the pharmacophore features for basketball, good basketball player. Okay, so what's the advantage? So later on, if I look for some tall people, I may consider them for my basketball team because you may think they could be good basketball players. So if I know what are the pharmacophore features of some molecules for which are showing some activity, okay, and then I look for in the databases those features, and if I identify some molecules, then I can consider them for that activity because I will think they will also have the similar activity. Okay, so like tall people may be good basketball players. That is the consideration we gave. So what are those pharmacophore features? Hydrophobic groups. Hydrophobic groups means CH3, C2H5, all those, hydrocarbon. That is hydrophobic. Aromatic rings. That's benzene ring, okay, naphthalene ring, that sort of thing. Hydrogen bond acceptors. Acceptors means nitrogen or oxygen without charges. Okay, nitrogen, oxygen. Hydrogen bond donors. That means NH or OH. Again, they should not have charge. O minus is not here. Hydrogen bond donor. It has to be OH. Cations or anions. That means sodium plus, Cl minus, all these are cations and anions respectively. So we specifically look only for these features: hydrophobic groups, aromatic rings, hydrogen bond acceptors, donors, cations, and anions. Okay, so if I have a set of molecules which is showing some activity, okay, then I will see what is the common feature of those molecules, whether they have common hydrophobic groups or common looking aromatic rings or common looking hydrogen bond acceptors or donors. Then I would say those features are necessary, or those pharmacophore features are necessary for that particular activity. Okay, so that is how I connect that actually. So we look at only these features: hydrophobic groups, aromatic rings, hydrogen bond acceptors, hydrogen bond donors, cations, and anions. Okay. So later on, I can look at a large set of database and look for those features. So if there are some molecules also having these features, then I would say probably those molecules have the same activity. Okay, that's the advantage. I can screen large database to see whether these features are present. So initially, I start with set of molecules which are known for some activity. I will superimpose their conformations and see what are the common features: hydrophobic groups, aromatic rings, donors, acceptors, cations, or anions, and then I identify those features. Then I'll go to any database and look for similar molecule with similar features. I pick them up and I will imagine that they will also have similar activity. So that way we can select molecules with the same pharmacophore features as the original set of molecules which have shown some activity. Okay, experimental activity, of course. Okay, that is what the pharmacophore based design is all about. Okay, so we will look at one example using this. Okay, so I have these are molecules. They are called selective cyclooxygenase 2 inhibitors. Cyclooxygenase 2 is an enzyme, COX-2 enzyme. It is found in the prostaglandin pathway of inflammation. So it is involved in inflammation. So that gives you a product called PGH2 that goes on into inflammation, pain, and so on actually. So there are drugs which are called selective COX-2 inhibitors. Those drugs selectively go and bind to that enzyme, thereby they prevent inflammation. So especially those who have arthritis, there is no cure for arthritis in old age. So these selective COX-2 inhibitor drugs are given, so they are able to control the pain and the inflammation. There are many drugs in the market. Okay, this is Validicoxib, Bextra, it's manufactured by Pfizer. Roficoxib, another name Vioxx, manufactured by Merck. Celecoxib, Celebrex, it's manufactured by Pfizer. Then there is another molecule which is in clinical trial, so there is no name for it. Okay, so all these have shown selective inhibition of the enzyme called cyclooxygenase 2 enzyme. Okay, so I want to see, is there a common pharmacophore feature for all these molecules? Okay, what are the common pharmacophore features for these 4 molecules? So there are some workflow, there are some free softwares which we can use to identify that. Okay, so what I will do is, first I will go to Zinc database. I will pick up the structures of these molecules. Okay, I have to get the structures of 3-dimensional structures of this molecule. Zinc gives it in SDF format. So I will go to Open Babel, then I will convert that into mol2 format. Okay, and then I'll put the mol2 of all these 4 structures into a zip file. Okay, then I go to a server called Pharmagist. This is the program called Pharmagist. I will upload this zip file, and then the results will come to your email. It will give you what are the common features, pharmacophore features of these 4 molecules. So this is the procedure. If you want, you can take a screenshot of, first I'm explaining the left hand side, then I'll go to the right hand side. We get the structures of each molecule from Zinc database. Okay, they will be in SDF format. We can download them. using OpenBabel, we convert into mol2 format, and then we'll put all the structures in one single zip file. Then I open a server called PharmaGist. I will upload the zip file, and it will come in my email the results of the pharmacophore features of these 4 molecules. If I want to view, I need this software, PyMol. PyMol is a software you can download. It's free for academic. It's free for students also. So you need to download this PyMol to view this pharmacophore features. Okay, you'll understand. So PharmaGist is a server. We upload these 4 structures in one single zip file in mol2 format. Results will come in your email. To view the pharmacophore, we need to download this program called PyMol. It's free for us, academic and students. Okay. So we will know what are the common features of these 4 molecules. Okay, that's how it is done. Once I have it, if I want to search databases to see whether there are other molecules with this feature, again there is another server program called Zinc Farmer. Okay, we can upload, and then it will pick out molecules from the Zinc database and tell us those molecules which have similar pharmacophore features. Okay. So it will give a lot of molecules. Then later on we have to run the SPCET to see whether those molecules satisfy the drug likeness property, and all those things actually. Okay. Lipinski's rule and so on. Okay. So we would have identified in the end structures, new lead molecule which has pharmacophore as this, which also satisfies all the drug likeness property. Okay, so those molecules may have similar COX-2 inhibitory activities because we selected those molecules based on the pharmacophore of reported COX-2 inhibitors only. Okay, and also they satisfy all the drug likeness property because we ran it in Swiss ADME also. Okay, so this is how the pharmacophore design works on. Okay, so we will be using the server called PharmaGist and Zinc Farmer. PyMol should be available on your machine, which you can download and then for viewing actually. So PharmaGist is a freely available web server for pharmacophore detection. Okay. So it does not consider the target protein. So it considers only the drug molecules. The input is a set of structures of drug-like molecules, okay, which are already reported for a particular activity. So here I am showing this picture, these 4 structures which are reported for selective cyclooxygenase 2 inhibition. Okay, so we start from that. That is our starting point. PyMol you can download. It's for visualization. It's a free for us, for students and faculty, open source. Zinc Farmer will search the databases actually. Okay, now we will start running that one by one. So we can get the structures of this molecule in SDF format from our so we'll search valdecoxib. Sometimes the names may be different also. Yeah, so this is valdecoxib. Okay, so you can see the structure. This is valdecoxib. So I can download the SDF format. Okay, there is another program which is called Marvin, MARVIN, which can view SDF files also. Okay, that's also free for students and faculty. Marvin, that's also free for students and faculty. It's useful. I will take some time later also. But if you want to see our ValidiCoxib, so SDF files can be seen through Marvin. So you can see this here. So you can see SDF files using Marvin. So Marvin is another useful software. I will talk about it much later. That is also very important. You should have that also. Okay, so I have now downloaded ValidiCoxib. Okay, now I go to your OpenBabel. So I have the ValidiCoxib, then I pull it out. This will be a clear screen or something. So it's SDF file format. Then I want to convert that into MOL2 format because Pharma just wants it in MOL2 format. So as I said, OpenBabel has everything conversion. So this is the MOL2 format. Okay. Initially, you will see it here down maybe. So this is ValidiCoxib SDF format. Okay. So if I convert that, let us see this here. Okay, try pause. So I can store it in MOL2 format. So it is stored here. Okay, so it is stored here. MOL2 format can be viewed by something called PyMol. Okay, for PyMol is another software which is free. You can download. Okay, it's free for us. Yeah, so as you can see, PyMol is a software which can see MOL2 format. So I showed you two softwares which are important for you to download. It's free for students and faculty for educational purposes. One is called the Marvin. We can view SDF files in Marvin. MOL2 files we can view in PyMol. Both the softwares we should have. So this is ValidiCoxib in MOL2 format. Okay, so I have the ValidiCoxib in MOL2 format here, as you can see. Okay. Sorry. Yeah, so first you go to zinc database. Okay, we took one of the structures, valedicoxib, and we got the SDF format. I downloaded that. Okay, and then I used OpenBabel and then converted into mol2 format. SDF format file we can view through Marvin, and mol2 format file we can view through PyMol. Okay, that's what I showed you now. Okay, similarly we can download each one of these structures, roficoxib, from zinc, roficoxib. Yeah. Okay, this is roficoxib. Okay, this is roficoxib. Again, I can download the SDF format. Okay. Is roficoxib. So we can view SDF format using Marvin, like I said. Using Marvin, and then again I use OpenBabel, convert that into .mol2 file. I convert that into .mol2 file. And then if you want, you can view it through PyMol. It's not that you have to view it, but if you want, you can view it into PyMol. Then you do the Celebrex. Again, Celebrex is also available in zinc database. Celebrex is the third molecule. Yeah, this is Celebrex. Again, I can download the SDF file. And then finally, we have the DUP697. That also we can download. Yeah, this is still not a drug. It is under clinical trials. That's why it does not have a name. So you can download the SDF format. Then we use the OpenBabel SDF to mol2 conversion, save it. Okay, so like that, we get the structures of all the 4 molecules. Okay, we get the structures of all the 4 molecules. So once we get the structures of all the 4 molecules in mol2 format, like I said, we need to put them in a zip file. Put them in a zip file. So I have done that. Okay. Yeah, 4 molecules in zip file. You can see this. All the mol2. I hope you can see this. Bextra, Celebrex, Dupe, roficoxib. Can you all see? Yeah, okay, so all the 4
Yes,
molecules, I put them into one zip file. Okay, 4 molecules I have said. Now I go to Pharmagist. That's the server program which I go to. It's called Pharmagist, and then I will upload the file. Pharmagist. Okay, can you see this Pharmagist web server? Okay. Uh-oh. Okay, so you can see here I upload the zip file, upload input molecules in mol2 format. So upload the zip file, then I give the email address here. Okay, then I'll say this choose file. I'll give that 4 molecules in our problem, and then you can mention how many pharmacophores you want to look at. We have only 5. Email address I give, and then I say submit. So it may take about 2 hours depending upon the. Okay, so I give submit. It's called Pharmagist. Okay, so it's running. So the results will come. The results will come in my email. The common structural features or common pharmacophores of these 4 COX-2 inhibitors. Okay, that's what. So it will come in my email. So I have to go to my email. Okay. Okay, so it takes time, 2 hours. That's why I have run it last night. So the results will come like this. Pharma results. Thank you for using Pharma. You can view your results under this. Okay, so I click on that. So it gives you, as you can see, Pharmagist results. The 4 molecules which I have given, it gives you some information about the molecules. These 4 molecules, and then it says, please look at this. I will make it bigger maybe. Okay, so as you can see that it gives you a score. Highest score means good fit between the 4 molecules. It has identified common 3 features. Okay, it has identified 3 features between the 4 molecules. What are the 3 features? They are 3 acceptors. Okay, it's also identified different 3 features, 6 features, 5 features, but the score is less. So generally we take one which has got the highest score. So it has also identified 6 features where 2 acceptors, 4 hydrophobic groups also, and it's also accepted 5 features. That means 3 hydrophobic and 2 acceptors, but score is low. So it's given different answers actually. Okay, different values. So generally we take the one which has got the highest score. Okay, so it has identified 3 acceptors which is common between all the 4 molecules. Okay, with the score of 11.9. We can even take this because 11.1 is not very far from 11.9, but it has identified 6 features there, 4 hydrophobic groups and 2 acceptors. More the features are, then you are restricting, and when you start searching for molecule, you will see much less number of candidates. Less the feature, you will find more number of candidates. Okay, so let us see what these features are. It says 3 acceptors. That means either 3 oxygens or 3 nitrogens or oxygen, nitrogen, like that. You know, that's called acceptor because acceptor is an oxygen or a nitrogen. Now we can save this file and then view it under py mode. Okay. Okay, so we can download this and then save it in our results. Yeah, so so these are the three features it's identified. So I copy that, so I can view them. I can get more details. Wait a minute. What are them? Label. So it's like we saw acceptor, it has got three acceptors. So we can see they are giving it as ACC. ACC is acceptor. So there are got three acceptors. Okay, so three acceptors. It's got, we can even get the distances from this of the each of these acceptor. So it's giving the distance, as you can see, between each of these acceptors. Okay, so it's given 8.3 angstroms between this acceptor and this acceptor. It's given 7.8 angstrom between this acceptor and this acceptor, about 1.3 angstrom. So it's like a isosceles triangle of three acceptors. Okay, at a certain distance, 1.8, 8.3, and 1.3 as such. Okay, now we can also superimpose those four molecules on top of this and see how they look like. Yeah, so we can superimpose. So each of those four molecules we can superimpose, and we can identify what those acceptors mean, which atom in the structure is giving us the acceptor. Okay, so you can see the other molecule. So there is that red color is oxygen. Okay. Yeah, so we can see the red color here, red color here. They are the oxygens. Yeah. So we can superimpose each of these four molecules on top of this acceptor, acceptor, acceptor. So nitrogen, the blue color is nitrogen, red color is oxygen. So nitrogen is also an acceptor. Okay, so if we go back to our PPT, okay, so these four molecules have something in common, three acceptors, either nitrogen or oxygen. That means you see two acceptors are close by and one acceptor is far by. That's why you get like something like a isosceles triangle. Again, you see in this, two acceptors, that is oxygen, are close by and one acceptor is far by. So it forms an isosceles triangle. Okay, two acceptors are close by, one acceptor is far away. You can see that actually. Okay. Here also we see 2 acceptors are close by the oxygens. Okay, so that is the common feature of all these 4 molecules, common pharmacophore. 3 acceptors like an isosceles triangle. 2 acceptors are closer and 1 acceptor is far away, almost 7.8 angstrom or 8.1 angstrom away. Okay, that's what it shows actually. So it shows that okay, so 2 acceptors are close by, 1 acceptor is far away, about 7.8 angstrom, 8.1 angstrom, about 1.3 angstrom. So that is the common feature of all these 4 molecules, which are cyclooxygenase 2 inhibitors. So acceptors means either nitrogen or oxygen, and similarly 1 acceptor is far, 2 acceptors are close. Okay, you can see this. So we used first the zinc database. We downloaded the structures in SDF format. Okay, we can view the SDF files using Marvin. Marvin is a free software, so for academic users. So we can get a, I think you have to get a license key. You write and they will give you a license key, and then you use OpenBabel, convert that into a mol2 format. Mol2 format can be viewed in PyMol. PyMol you have to download. So Marvin you have to download, PyMol you have to download, and you can view the files in PyMol. Then we put all these 4 structures, Mol2 files into a zip. Okay, as I showed you here, I put them into a zip. Yeah, these 4 files into a zip format. Okay, and then what did I do? I went to the PharmaGist. I uploaded the zip format. Once I uploaded, it comes through email, the results. So the results, it gives you various scores. We took the topmost score, and we viewed that topmost score inside the PyMol. Okay, we viewed that inside the PyMol. So we found out it's got 3 acceptors. You can see 3 acceptors, like an isosceles triangle. 2 acceptors are close by, and 1 acceptor is far away. Okay, so these are the common features of these 4 molecules. Okay, so you can see 2 acceptors. Nitrogen or oxygen is called acceptor. 2 acceptors, 1 acceptor. 2 acceptors, 1 acceptor. 2 acceptor, 1 acceptor, like that. 2 acceptor, 1 acceptor. So that's the common feature of all these 4 molecules. So if I look for similar feature in my database, 3 acceptors at about 8 angstrom, 2 of them about 8 angstrom distance, 2 of them close 1 by 1.3 angstrom. If I find some molecules, probably those molecules also may have cyclooxygenase 2 inhibition property. Okay, so that is the logic. So what do we do? There is another server called Zinc Farmer. So we have to use that to do the search. So we give the input from the PharmaGist to the Zinc Farmer and ask it to look for structures in the Zinc database. You can even create your own database later on, but I'm showing only Zinc database, and it will identify molecules with the same feature. That means in our case, 3 acceptors, 2 of them at 8 angstrom and 7.1 angstrom and 1.3 angstrom. So we have to use the Zinc Farmer. Okay, Zinc Farmer is another one which we use now, which can search Zinc database for the same feature. Okay, this is the Zinc Farmer. Now we have to upload the output which we got from our PharmaGist. Okay, we have to upload that. Okay. Okay, here we say load features. So we load 3 4 features. So we load it. And, okay, so as you can see here, it has superimposed all those 4 molecules which I showed you: Celebrex, Vioxx, Rofecoxib, DUP6, and these are the three pharmacophores: acceptor, 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 like a triangle. So it has uploaded, you see, hydrophobic, hydrogen bond acceptor, hydrogen bond acceptor, hydrogen bond acceptor. Okay, so that is the result we got from a PharmaGist. Now we loaded this into the zinc format. Now we can ask this software to look for similar structures in zinc database with this feature. That means 2 acceptors at 1.3 angstrom, 2 acceptors as 8 angstrom and 7.3 angstrom. Yeah, 7. Yeah. So I can say submit query, so it will look for similar features available. It will take a long time because the zinc database is a huge database, so it may come up with lakhs of molecule, but later on we can it will arrange them in RMSD. RMSD is root mean square deviation, so smallest RMSD. Then later on we can apply our filters, ADME filters. Like we can take the structure to Swiss ADME and see whether they satisfy all the conditions of drug likeness, sorry. So if it does not, then we can reject that. Okay, so we will say submit query. So you can see it is doing, it will take a little time. Oh, not bad, it did fast. It gives you the RMSD also here. That means the root mean square deviation of that molecule with this feature. So we can arrange them in the lowest to the highest RMSD. So you look at this structure, this has got the lowest RMSD. That means it is closest to the acceptor distance of 7.3, 8.1 and 1.3. Okay, this is the closest. Let us look at what that molecule is from our zinc database. Okay, so it is arranging lots of molecules. As you can see, got almost 6 million hits. But of course, some of them might not satisfy Lipinski's rule and ADME rules and so on, actually. So we need to look at that. Maybe some of them. Okay, so let us look at the structure. So it will look at the structure in the zinc database. Okay, this is the molecule. So it's got 3 acceptors at whatever distance we have talked about. So this you can see oxygen, oxygen, nitrogen. So like a triangle. So this is the closest. Zinc 9,4. This is the molecule, it says. Which has got the same feature with the very lowest RMSD. Okay, now we need to know whether it satisfies all the rules. So what do? We go to Swiss ADME. Okay, then we copy the smiles notation. Smiles notation is here. And then I will enter the smiles notation. And then I will see whether it satisfies all the conditions. So, yeah, so it's done the calculation. So okay, this is the molecule. Let us see molecular weight 477. Then let's look at log P 2.6, not bad. GA absorption is low, so it's not very nice. Blood-brain barrier penetration. Lipinski's rule, it satisfies all the rules, but Gauss et al. Rule, one violation is there. Weber rule, one violation is there, because polar surface area is greater than 140. It's got too many. You can see it's got too many oxygens, nitrogens, oxygen, nitrogen, oxygen, nitrogen, nitrogen, nitrogen. So it's very polar molecule. As I said, if it is too polar, it will be good water solubility, but it will not penetrate very well the GI, because GI is made up of lipids, your tract, intestinal tract. That is why GI absorption is low, because PSA is very high. PSA means polar surface area, total polar surface area high. Bioavailability is good for 55%. GI absorption little bit low. Solubility will be very high because it's got a lot of nitrogen, oxygens, and so on. Log P is 2 point something. Okay. So it's not a bad molecule you can think of. So it gives a lot of information about cytochromes. Cytochromes are the oxidoreductases present in us, which degrades molecules. So you know, let us look at the BBB penetration. No, it does not penetrate BBB, not bad. Molecular weight is 477. So if we add more atoms to it, molecular weight may go to 500. And as per Lipinski's rule, above 500, that's not good. Okay, so Gauss et al. Rule. So generally, polar surface area is high. All the rules are, it is violating Weber rule, Egan rule, Mukesh rule, because PSA is high. PSA here is, wow, it's quite high, 154. That's very, very high. We need to bring it down to less than 120. Ideally, I said about 80 to 120, 130 is good. So some of these OHs and all has to be removed. Okay, that's the best. If you remove some of these OHs, PSA will come down, and these rule violations also may go down. So if you have a medicinal chemist or a synthetic chemist sitting next to you, he or she can suggest how to reduce some of the OHs present. We don't add new groups because molecular weight is already 477. We don't want to cross 500. Lipinski's rule will not be satisfied. So ideally, we'll try to remove some OH, that is phenolic OH groups, so that polar surface area comes down. So this is a strategy. Now let's look at the second molecule in that list. Okay, that's first molecule. Let's look at the second molecule. Yeah, in that list, which also has good RMSD. Okay, the second mass is quite low. Unlike the first one, mass is high. This is mass is low. Let's look at that molecule. Okay, so you see again, it gives you, okay, yeah, oxygen, nitrogen, that's close acceptor and one acceptor far away, exactly matching our pi mole picture. Yeah, exactly matching our pi mole picture. Not two acceptors nearby, one acceptor far away. So here if you see two acceptors nearby, one acceptor far away. So it's identified another molecule. Hopefully this may also have activity. Let's look at some of the properties. PSA molecular weight is quite low. pH, the hydrogen bond donors, acceptors is 75. This is not bad. Polar surface area is reasonably okay. Now let us look at the other properties. Let's run Swiss ADME. Let's run Swiss ADME to see how the numbers look like. This is much smaller molecule. It's got a lesser polar surface area when compared to the previous one, which much smaller. Okay. Okay. See, GI absorption is very high, very good, and all the rules are satisfied. See, so better instead of taking the first molecule, which has got the lowest RMSD, I would prefer the second molecule because it satisfies all the rule. The G absorption is also high. It's less polar. The previous molecule had very high total polar. See here, it has come down to a very small number, okay, 103. Whereas this first one had very high polar surface area, so the Ga absorption is very low. It did not satisfy many of the rules. Whereas the second molecule in that list looks good. It satisfies all the rules. Polar surface area has also come down. Ga absorption. So this could be a good candidate. It has the pharmacophore features of those drugs, reported drugs, that is acceptor, okay. It has all the pharmacophore features of those 4 drugs, which are called cyclooxygenase 2 drugs. That is the acceptor at about 1.3 and it's 1.8 and 8.3, as well as it satisfies all the drug likeness property, ADME properties, okay, bioavailabilities, and as you can see here, the bioavailability is also good. Polar surface area is also within range. It satisfies all the rules: Mukesh rule, Bose rule, Weber rule, Lipinski's rule. GI absorption is also good. So this candidate appears to be a better bet as a oral drug than the previous candidate. So we can keep this as a possible. Like that. Okay, like that we can go through the entire list and select maybe 10, 20, 30 candidates which satisfies all the rules, which appears to be good, and then we can maybe buy these molecules, or we can synthesize them and then do the in vitro experimental studies as a possible COX-2 inhibitor. So this is how the whole flow will be. Okay. So hopefully these candidates may have COX-2 inhibitory activity because they have the same pharmacophore features as the 4 reported drugs, because those drugs are reported. Okay, 4 reported drugs. Okay, 4 reported drug. These are the 4 reported drug. Same pharmacophore features, and they satisfy all the rules of drugability, all the rules of ADME, the bioavailability, GI absorption, and so on. So, and this is the entire workflow for pharmacophore based design. So we select the molecules in zinc database. Suppose the molecule structure is not available. What do we do? I will teach you later. But the zinc database has about 200 million molecules, so you should be able to find. Suppose you do not have the 3D structure, we can use Marvin. I will show you later. So we get the structure SDF file. We can look at the structure if you want using Marvin, which is a free software. Then we convert into MOL2 format using OpenBabel. MOL2 format files can be looked at using PyMol. Okay, and then we put all the structures into a zip file. Then we go to PharmaGist. Okay, so I showed you how the PharmaGist looks like. Okay, so we look at the PharmaGist. PharmaGist, and then we give the information as a zip file into PharmaGist. The results will come to your email. We generally select the top hit based on the score. We can view the whole thing using PyMol. In this particular case, we found out it's got acceptor at certain distance. Okay, this is called the pharmacophore features of those common pharmacophore features of those 4 molecules. Okay, and then PyMol is a very useful software. We can do a lot of things. We can look at structures and so on. Okay, so we can look at many things with PyMol. PyMol is useful for viewing .mol2 file. PyMol is useful for viewing results from PharmaGist. It's a free software as well. So okay, once we have the feature, we can use another software called Zinc Farmer. We upload this particular set of features, and it searches for similar structures. Okay, that's the Zinc Farmer, and then comes up with possible candidates which have similar structure as this acceptor. Here you can see acceptor, 8 angstrom, about 7.38 and 1.3. So RMSD. So I looked at the topmost hit, which is close to that. I found out it's not satisfying the ADME bio rules, and it's got too much of very high polar surface area. So I went to the second molecule, and second molecule looks very good because it satisfies all the rules, as you can see here. Good GI absorption also. So according to me, that's a better candidate than the first molecule. Then we go to third molecule. Then we do the same thing, and then select or unselect. Then we go to fourth molecule. Like that, we can go through until we get about 10, 20 molecules, which appears to be good candidates, having similar pharmacophore as well as the ADME bioavailability rule satisfied. Then we can synthesize all of them. Okay, we can synthesize all of them and check the cyclooxygenase 2 activity, and hopefully some of them or many of them will show good activity because we selected the same pharmacophore. Thereby, the whole procedure is you are coming up with new structures which has not been reported so far from the existing structures, drugs which have shown certain activity against cyclooxygenase 2. So you are coming up with new structures. So possibly new structures means it can be patented, but old structures cannot be patented. Even derivatives of old structures cannot be patented, or modification of old structure cannot be. But if you come up with totally new structures, then which is not in that list of cyclooxygenase 2 inhibitors, you may be possible to patent them. Okay, so generally we go to Zinc database to get the 3D confirmation of the molecule, okay, the SDF file. But Zinc database has millions of structures, so generally you will find. But as a chemist, if you start designing new molecules and synthesizing new molecules, maybe you will not find the structure. Then what do I do? How do I get the 3-dimensional confirmation of a molecule which is totally new? There we can use Marvin. Okay, so Marvin Sketch. This is a free software. Okay, so here we can draw a new structure, totally new structure. So as a chemist, you have designed a new structure, and Zinc does not have that structure. So I can draw that structure totally, and then later on I can get the 3-dimensional confirmation of that structure. That's called the minimum energy confirmation of the molecule. Imagine I'm drawing a new structure. As a chemist, I am coming up with something new. Okay, which is not there in either Zinc, or you can even search other databases to see whether that structure is there. Imagine it's totally new, which you have done. I'm drawing something where the structure is already there. This is called a chalcone. But imagine, so you can draw the new structure, which is not there in the okay, which is not there. Okay. Okay, then this is on the paper, so it is like a 2-dimensional sketch. But I want to get the 3-dimensional confirmation of the molecule. So I have to do the 3-dimensional confirmation. So what we do is we go to structure, Then we say clean in 3D. So it gets you the 3D structure, clean in 3D. Okay, and then we can say confirmation. So it will get the three-dimensional minimum energy confirmation. That is the confirmation which the molecule will attain so that the energy is minimum. Thermodynamically, all structures in vacuum will attain a minimum energy confirmation so that the delta G is minimum. Okay, but in solvents or in some other medium it can change, or in presence of something else it can change, but in vacuum, for example, it will try to attain a minimum energy confirmation. So we can get that minimum energy confirmation of this molecule, which I have drawn here, okay, using this particular command. Yeah, so it says it will. Okay, so it's got some confirmations, as you can see here. This is the confirmation. This energy is 47 kilocals per mole. Then it's got minus 47, of course. And then it's got some other numbers, different confirmations are there with different numbers. You can see some 57 is also there. So I will select the one which has got minimum. This one. Okay, so it's got 47 points. So I can save it as SDF file, and then I can use it for my studies. So if I have a new structure which is not there available in Zinc, this is how I do. I go to Marvin, sketch, then I draw the structure, and then I do confirmation, calculation, then it will do a confirmation calculation and get me the confirmation of the molecule in 3 dimension. Then I can save this file as SDF for mol2 format, and then I can use it for my pharmacophore studies, or later on if I want for docking also I can do it. Marvin is a very useful software which can do all these calculations. Okay, getting the 3-dimensional confirmation. It can also calculate properties. For example, this is a new structure. I want to know the log P, okay, partitioning log P of this molecule. So it will calculate the log P also. So it can do many property calculation also. Okay, so log P is 3.89. So it is this log P calculation is based on group contribution method. So for each of the atoms it gives a log P, so there will be a database, then it adds up. So oxygen is there, so it's a negative log P because it's very hydrophilic. All the carbons have positive number, so it adds up and comes out. So this is the log P of the molecule. You understand? So this Marvin can also do a lot of calculations, like I said. It can also calculate polar surface area. If you are interested in knowing the polar surface area, it can give you polar surface area, because generally polar surface area should be about 80 to 120. Polar surface area is about very low, because it contains only carbon, aromatic. Only one oxygen is there. That's why it's given very low polar surface area. Okay, so chalcones are not water soluble, and that's the problem with chalcones, because they are very hydrophobic. Then it can calculate pKa values, geometry, topology analysis, geometry descriptors, molecular surface area. So all these descriptors. So it gives you a lot of other properties: projected area, length, perpendicular, so many other properties. They are called geometric properties. So it can calculate some descriptors or properties. Van der Waals volume, again, volume is useful if you are talking about drug going and binding to an active site. So the active site volume and drug volume should match. Okay, so those are all called geometric descriptors or geometric properties. And then it can also calculate charge distribution on the molecule. Yeah, this is the charge. So negatively charged, your oxygen rest all, or positively charged. Of course, there is one negative. Some negative charges are coming because it needs to be balanced here, positive, negative. As you can see in this aromatic group, which is closer to your oxygen because of oxygen. So here, if you see, the red color is negative and the blue color is positive. So some negatives are coming here because of this particular oxygen, whereas here there is not much. So it can calculate charge distribution also if you are interested in electrostatic calculations. Okay. And then it can calculate pKa value. Yeah, protonation, pKa value. pKa is useful, like I yesterday mentioned. It tells you the pH at which dissociation takes place. Stomach has a pH of 2. So if you want fast acting drug, it should not dissociate in stomach. If it dissociates, it becomes plus minus, which is very charged. It will not cross the GI. GI is very, very lipophilic or hydrophobic. So if it doesn't dissociate in stomach, it will get absorbed in stomach. If it dissociates in the stomach, it will not get absorbed. So it will get absorbed much downstream. Okay, so acidic drugs can get absorbed. Okay, whereas basic drug. Okay. I don't know why it's not doing. So acidic drugs will not dissociate in stomach, so they can get absorbed fast. So if you are looking at fast acting drug, try to design something like that. So if you have basic drugs, if they dissociate in stomach, they will not get absorbed in stomach, but they will get absorbed maybe down into the small, large intestine and so on. Actually, so no ionizable atom form. Okay, it cannot be ionized because there is nothing there. Everything is hydrophobic. CH carbon carbon, only oxygen is there. If it is OH, of course you will get some O minus and H plus, whereas this is a double bond O, so obviously there is no ionization possible with charcoal. Understand? So it cannot have a pKa at all because there is nothing to get ionized. Okay, that's what it says. Okay, agreed. So this is rofecoxib. So this is rofecoxib, as you can see here. Okay, then we can this rofecoxib. So we can draw the conformations. So we can get the conformations and also the minimum energy conformations. Okay, so this is rofecoxib. You can see the structure here. We can, like I said, we can get properties of these geometrical properties, molecular properties, conformation details. You can get the charge distribution. Yes. Okay. So this charge distribution on methoxib, all the negative charges are given as a red color, positive is given as, okay, all the C carbons will be in blue color, oxygens, nitrogen, given like this. So you can see oxygens here. This is the log P of ferrofucoxib. You may find some difference in log P between each software because each software may take different assumptions in calculating log P. So try to use the same software if you are testing many compounds in one group. So don't use different software for calculating log P if you have one group of compounds. So if you are having 20-30 compounds, you want to do some study, use the same software for all the calculations. Okay, that's very important because there could be some difference in log P between softwares because each software has different approaches in calculating log P. After all, these are all calculations, so they have different databases, different approaches, different equations for calculating. Okay, so this is the log P, and this software does it based on group contribution method. That means depending upon group, each group has certain number, it adds up. So oxygens means negative number, some number, or CH groups has some positive number. So it adds up. So you can see negative, 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 and the rest are all positive. So it will add up and come up with this. This is called group contribution method. Some softwares use structure property relationship type of equations. So different methods are there actually. So don't use different softwares to calculate log P for a same set of molecules which you are studying. Okay, so Marvin is extremely useful for you if you do not have the conformation of the molecule, new molecule which you have designed in your lab. Otherwise, most of the structures you may, three-dimensional structures you may find in zinc, or if you go Google search and find. But if you are designing your own molecule and the structure is not there, you use Marvin. Marvin is a free software, so you can draw the structure. You can get the minimum energy conformation, which I showed you here. To get it, can also calculate some properties. So we can save this file, use it for your pharmacophore modeling, or use it for docking studies later on. All these things can be done using Marvin. Okay, so today I showed you a lot of new things which are freely available softwares, okay, which can be used for many of your studies, okay. And then we combined it with the knowledge which we had from yesterday, that is the bioavailability, ADME, drug likeness property, and so on, okay. Thereby, you come up with possible new candidates which will have the same pharmacophore features as the known drugs for a particular disease. So hopefully, they may also exhibit similar properties. So today we looked at PharmaGist, which can do a pharmacophore search. PharmaGist, you upload the mol2 files in a zip file, and the results come out in your email, and then you can view them using PyMol. Okay, you can view them using PyMol as here. Okay, in our problem which I showed you, the results are okay. In our problem, we looked at these 4 different structures. we wanted to see what are the common pharmacophore features. So pharmacophore features means hydrophobic groups, that is CH2, CH3, C2H5, they are called hydrophobic groups. Aromatic, that means benzene rings. Hydrogen bond acceptors, that means oxygen or nitrogen. Hydrogen bond donors, that means NH or OH, or polar groups, okay, anion cations, okay, sodium plus chlorine. So pharmacist looks for common these factors. So the results come in your email, so we can take the top here, highest score, and then we can take it to bimole, and then bimole shows you what are those common features in this. So in this particular problem, we said the common feature is 2 acceptor close and 1 acceptor far. 2 acceptor close, 1 acceptor far. 2 acceptor close, 1 acceptor far. You can see 2 acceptor. So that is the common feature in all these 4 molecules. So we use another software, online software called Zinc Farmer. It you upload the features, and then it looks for similar structures with those features in the Zinc database, and then we take those molecules and see whether they satisfy all our ADME rules, the bioavailability rules, drug likeness rules. We use FRIS ADME, or we can use pre-ADMET. If something, one molecule doesn't satisfy, don't use it, because ultimately it may have poor GI absorption or something. So in our example, like we saw, the top molecule did not have the features. So we took the second one, and it had all the features. So that could be a possible candidate. Like that, we can keep on selecting many candidates. So we come up with possible candidates, then we can synthesize them, and then we can test them for cyclooxygenase 2 activity. So that is how we go about. So the starting point is some known, reported, experimentally reported inhibitors for a particular disease, and then we develop a formula. Okay, so what happens if the structure is not there in Zinc or any literature or any open source? We can use Marvin. Marvin is also a free software. We can draw the structure, and then we can minimize the energy and get that 3-dimensional conformation. As I showed you here, we can get the 3-dimensional conformation of the molecule, okay, and then save it as SDF file. So this is also very useful. So Marvin is a free software you can download. Bimole is a free software. OpenBabel is very important. Pharmagist, okay, and Zinc Farmer, we use it online, and we get the results. Okay, so I think. Okay, now so we looked at only ligand-based pharmacophore. That means we don't know anything about the target protein or structure. So ligand-based is what I will focus on. So it's useful in the absence of target protein or enzyme. Okay, so we know some molecules which have been shown to have certain activity. So we superimpose all the molecule and get the pharmacophore. There is also something called target-based pharmacophore. It's coming up slowly now. That means you know the 3D structure of the pharmacophore and the ligand, various drugs go and bind, and you, based on where it goes and binds, which particular area, we call that that interacting area is very important. So we identify some new molecules which will go and interact there only. It's called target-based pharmacophore. Okay, so there we need to know the 3D structure of the protein or enzyme. We need to know the active site and where your drugs and go and bind. So that area features, that is called target-based pharmacophore. So we will not talk about it. Our focus is on ligand-based pharmacophore. Okay, so that is what I will talk about. This target-based is coming up slowly, but there it complicates the issue, because we need to see where all your ligands go and bind into the target region, and then you say those target region is very important. So whichever new molecule goes and binds, then we will consider that as a possible candidate. So that's called target-based pharmacophore. Whereas whatever we talked about today is all ligand-based pharmacophore. So here we superimpose the 3D structures of all the ligands known for some activity. Here in my example, I showed you cyclooxygenase 2 activity. So we can look at several activities. So if you are designing molecules for angiotensin converting enzyme, it is involved in hypertension, ACE. If you are designing drugs for ACE, look at those drugs, superimpose and try to find some common features. Like that, you can look at different types of pharmacophore. So angiotensin converting enzyme, we have many drugs which are there in the market related to angiotensin converting enzyme blocking. Okay, so they are called captopril, enalapril, fosinopril, ramipril, zufinopril. So all these are angiotensin converting enzyme inhibitor. Okay, so we can see the common features of that also in the same way. So I have put them as a mol2 file. Okay. So I have put all the structures into, like I said, into a zip file, and then I ran the pharmacophore. Then I got some results, and then it came up with 4 possible pharmacophores. Okay, so it will have 2. I think. So it's got a. So the angiotensin converting enzyme inhibitors have a different set of pharmacophores. Okay, so it's got 4 pharmacophores, as you can see here. Acceptors, then it's got 2 hydrogen bond donors. Okay, so 2 acceptors, 2 hydrogen bond donors are there actually. So like that we can do for any system. You pick up drugs which are reported for certain disease, and then get the SDF file, convert into mol2 file, put them in zip, run the pharmagist, and then you get the results, and you can view them in PyMol to get the common features of this. And then if you are interested in designing new possible molecule, go to Zinc Farmer and try to pull out structures which have this particular feature, and then you check for the bioavailability, ADME properties, and then GA absorption, satisfying all the rules and so on. So this is the entire procedure. Okay, I think I will stop with this. If there are any questions, you can ask. Tomorrow we will talk about some other ligand-based design.
Thank you so much, sir, for explaining us about pharmacoligand-based designs. As the session gets over, participants can ask their queries.
Good morning, sir.
Good morning.
When we create a new drug, then how can we, like as you said in the Marvin sketch, so how do we derive the SMILE notation, and how can we check the drug lightness or toxicity?
Yeah. You draw the structure in the Marvin sketch.
Yeah.
Okay.
Yeah.
And then we can get the 3D confirmation, which I showed you. Okay, confirmation, search, and all that.
Yes.
Okay, and then we can say file, save as. It's got different save as options actually. Okay. Okay, it's got different. You can see here.
Yes, sir.
So we can save it, and then we can use Open Babel to convert into whatever format we want.
Okay.
Okay, and then we can go to Swiss ADME to get more properties, or we can take it to ADMET, pre-ADMET, or ChemDesk. So we can do all those things. So we can save it in many formats. Okay.
Okay. Okay.
And then any Open Babel is there, which can convert anything to many formats. So any file we can also convert into smiles to mol to mol to everything. Okay.
So you mean like after we create this sketch, we can convert that into SMILE notation?
Yeah. We can. No, here we want to get the 3D structure. So we get the 3D confirmation. Then I can save it as a SDF file itself, because if I want to go to Pharmagist, I need it in SDF or I need in mol2, right? So I need to save it in SDF format, not in SMILE notation. Understood?
Okay.
Okay.
Yes.
Yeah, see here you have the mol, all the formats are there. But for a 3D confirmation, it has to be in SDF format, or it has to be in mol2 format. For Pharmagist, we need to have in SDF and mol2, not in Smiles. Smiles, we use it for calculation in Swiss ADM.
So
Property
property
calculation. Yeah.
Sorry to interrupt you, sir. How do we get the toxicity check then after saving it as SDF file?
Yeah, you save it in SDF, and then SDF to mol format, and then pre-ADMET takes mol format, .mol.
Okay, sir. Thank you.
Okay, so you see in the save as, it's got SDF format also. Marvin sketch, you can see this here.
Yes, sir.
So you can save it in SDF, and then go to Open Babel, take it in mol2, and then go to Pharmagist. Okay.
Okay. Yeah. Thank you, sir.
Thank you.
Thank you very much.
And then Swiss ADME also takes it in many formats, not only Smile. Swiss ADME import command is there, so it will also take it in many formats. I'll show you Swiss ADME. It takes in many formats. Yeah, import command is there. You see, import.
Yes.
You can see here.
Yes, sir.
Many commands are there, right? Can you see this?
Yes, sir, I could.
So you can import in many formats, structures. So that lot of flexibility is there between these softwares.
Got you, sir. Thank you.
Okay, any other question?
Sir, I do have one more question, sir.
Yeah, sure.
Is there any tool to check the antibiotic resistance of a drug?
Antibiotic resistance is because of 4 different or 5 different reasons. That's a very general statement. It could be because of blocking of purines. It could be because of change in the target site. It could be because of efflux pumps. So 4 different reasons. So if you know specifically, we can do docking. So if it is because of efflux pumps, then we can design efflux pump inhibitors which will block the efflux pump. So exactly you should know. So antibiotic resistance is a general term, but we should know the exact mechanism. Okay, like I said, there are 4 or 5 different reasons why antibiotic resistance can happen. So if you know, then we can think of the target and designing molecules for that, inhibiting that target.
Okay, sir. Thank you.
Thank you so much, sir.
Okay. If there are no questions, we will close the session.
Yes, sir. The session was very informative.
Okay. We will close the session.
Thank you, sir.
Thank you.
The attendance link is provided in the chat box. Those who haven't marked the attendance, you can use that link to mark the attendance. The feedback link and the attendance links is same. You can give your feedback on the attendance link itself. Thank you all the participants for attending today's session. The participants are asked to practice these softwares and concepts you have learned today. We will continue the session tomorrow. Thank you.